All right, hello everyone. This is John, and today I'll be covering part 2 of the Longitudinal Multilevel Modeling series in RStudio. As previously outlined in the first video, we covered the unconditional means model, which was the null model, really just testing the intercept and grand mean along that y-axis for job performance. What I'll be doing in this video today is now covering the unconditional growth model, which is really going to involve setting up the slope. For this video, I'll be testing two different types of slopes, the fixed slope and the random slope. The fixed slope makes the assumption that everyone within your data is following a similar pattern, a certain pattern of progression over time, let's say. Perhaps all increasing over time or perhaps all decreasing over time. Whereas a random slopes allows for that individual variability, meaning individuals might have unique traits amongst themselves, so their levels of progression might vary quite widely, meaning they might increase, they might all decrease. There's a lot of variability that could be happening. So in that first video, video 1, I covered the unconditional means model, which showed to be statistically significant from 0. The intercept was quite high, and here's those upper and lower values. And then really what I'm going to be doing today is now putting together that slope. So based on the intercept, which is 5.05, now we're going to be testing the slope to see whether it'll be fixed or random. So to go quickly back to the research question is really asking how much a 4-session on-the-job training will improve employees' job-related task performance. The on-the-job training took place at 2 different job sites, and employees rated their satisfaction with their trainer and rated their overall job satisfaction as well. So in the first video, we only covered one element of this research question, which is job performance, which is really the dependent variable within this study. Now that we have job performance already within the model, now we can actually include a time variable now, which will be days of training, which, as highlighted here, everyone took part in various different days of training. Some took part in all 4 sessions, some only took part in 1. But regardless, we're going to be measuring days of training, as that's going to help us set up the slope for our study. So just like the slide I showed just earlier, this one, we're going to test now whether along that x-axis, days of training, is best represented as having a fixed or a random slope. So that is pretty much exactly what the research question is. Let's test both, and then after running both, we can compare those now with the first model, the unconditional means model, to really see which one significantly differs based on model fit. We'll compare the fixed slope to the unconditional means model, and then we'll compare the random slope to the unconditional means model to see where that significance truly lies. So let's jump over to R. Right away, you want to get the data set in, which it is from before. So I already have data already inputted. I can click it here. Here's the data, just like the last video. Want to make sure we have the nlme package ready, which it is. And then, of course, we could just look at the headers of the data just to make sure everything looks the way it should. So now this is where we start getting into the parts involved in the unconditional growth model. The first thing we probably would want to do is begin actually plotting the data to see what individual slopes look like. Because we want to determine whether time or days of training should represent a fixed or a random slope, we really just need that opportunity to visually look at the data. And that's what I'm going to do now. So for this, I'm using another library, which is called Lattice. If you do not have it, install it. And if you do, you can run it. So I'll do that. And now I'm just going to run some simple plots here, looking at the dependent variable, which is job performance, across time. And time is really just days of training. And for each plot, I want individual plots. So there will be a series of plots, and they're all coming from that data set. So I will run this now. Just waiting for it to load, and here it is. We can click zoom, and really here are all the individual plots at this point. So there's of course many other predictors that are involved in this study, but a lot of those other predictors won't come until in the next video, the last video of this series. So here right now, we don't really know what individuals were a part of certain job sites or what their satisfaction was with their trainer. But by just looking at, I'm just moving this over just a tad, but by just looking at days of training and job performance, we can see that there's some individuals who seem to decrease over time, which is very evident in these first few rows. But then we have individuals who do the exact opposite, where they increased over time. And you could see for some individuals where there's only there's no actual line, regression line, those are the individuals who only completed 1 day of training. But just by the overall landscape, which of course this does not include all the participants from this sample, this is just sort of like a small sample of what the plotting would look like. Similar to what I did with the longitudinal in this thing here, it's just grabbing little windows of the data. But you could see here that we have some variability going on. So in this case, to have potentially a fixed slope compared to a random slope would show probably quite different results. But let's run both because we want to see really what each one would look like with such variability in the data. So I'll just exit this, don't need that. I just want to clear the space. So now we can move into the next step. We're going to run both unconditional growth models. The first one, we're going to treat days of training with a fixed slope, which is really saying that everyone should be progressing in the same direction, which we clearly see they are not, but we'll see what it looks like. And then the next one we're going to run as time or days of training as a random slope, which accounts for individual variability. And let's see which one best fits the data. So for this one, we call it mod 2 because mod 1 was the unconditional growth model. We have job performance, and now we're including the fixed slope, which is days of training. Here you could see the random is 1 because we're not including days of training as a random slope here. We're including it as a fixed slope. And of course, we're running this across individuals. So we can highlight this with summary mod 2. We can click run. And here we are. So here's the log-like value. It's still pretty high, and if you recall from the first video with the unconditional means model, it's almost identical, but we'll compare those a bit later in this video to see whether it's significantly different from the unconditional means model. And then of course we have these other values here which can help us to calculate that intra-class correlation coefficient. Ideally, if we're accounting for a lot of the clustering with the slope, the intra-class correlation coefficient should decrease over time. But we're going to compare that once again at the end of this video to see what it looks like between the original model, which was the unconditional means model, and these two models which I'm demonstrating here to see how those values have changed. So the more important part, and the thing we want to look at and take account of right away, is this fixed effect. We have job performance with a fixed effect of days of training, meaning this is the fixed slope. Days of training is fixed across individuals, and right away, just looking below the p-value, it's not significant. So creating a fixed slope for these individuals is not actually capturing the fit of the model, really. It's not a good fit, and it's very evident here because it is not significant. Let's go back up. Let's run the intervals to see what those look like. So here we are, and as I was mentioning in the first video, sometimes it's hard to tell whether these intervals are significant or not, especially if you're not used to looking at confidence intervals, and because there's no p-value attached to these. Of course, for the fixed effects, we do have that p-value, which is right up here. This is it right here. Oh, I should slide up a bit more. It's not significant, and when we look at those confidence intervals, we can see they're not significant. This one hangs just below 0, and these two values are now above 0. So it goes to show it's sitting on that cusp. It's not significant. Time as a fixed effect, or as a fixed slope, sorry, is not significant. But what's interesting though, if we look at the random effects, these are actually still significant, meaning there's still a lot of variability that needs to be accounted for within the model, and we can still capture that variability. So even though the fixed effect is not significant, we could see right away that the random effects are. And that's promising because that will help us then know that maybe there's other ways we can better structure that model, which we're going to do now up above, where we're going to run the unconditional growth model once again, which will be mod 3 this time, and we're going to include time or days of training as a random slope. So let's clear the space here, and let's quickly go through mod 3. So we have mod 3. We're going to look at job performance, and it says days of training here because that's what we're comparing it to, but what really matters is this part right here where it says random days of training. So whereas in the above model, random equaled 1, which is now fixed, here random equals days of training. So for each individual, we're allowing days of training to vary, meaning maybe for some individuals, their job performance based on days of training might go up, and maybe for some individuals, based on their days of training, their job performance might go down. We're accounting for individual variability now, and that is what we're doing by having time as a random slope. So let's run this now. And here we are. The log-like right away from the first model we just ran, the fixed slope, it was 179, and now we can see that it's 161. So already there's already a better fit being demonstrated within the model. And then of course here are these other values which we are going to account for as well, and these are going to help us to calculate that intra-class correlation coefficient. But an important thing to mention here is that when you look at these fixed effects, right now, days of training, it's not significant because for that sole purpose that it is not a fixed effect. It's not a fixed slope. But what we know though is by including days of training as a random slope, let's look at these intervals because that's going to help us determine it, is that it is significant. So if we go under random effects here, we can see that for days of training, it is significant right here. And this is an interesting thing here. It's showing here that the intercept in days of training, it's not significant here, but that's also accounting for that. It's accounting for that individual variability, meaning some people are dipping below 0 or the intercept, and some people are going above the intercept. So really, this value here is a bit deceiving because it's saying it's not significant, but it's really just trying to depict that a lot of it is going all over the place across our intercept. But what we know that by including time, where is it, as a random slope, our log-like has dropped, and now we can compare these values to see which one is a better fit for our model. So I'm just going to clear the space again. So yeah, as I wrote here, the two groups sharply contrast in their performance based off training performance over time, which we saw in the plots, and hence why right away we could see from the log-like value that having time as a random slope was definitely a better fit for the model. So at this point there might be some confusion because days of training was not significant in either model for fixed effects, but right away by including it as a random slope, the log-like did drop. Some things that might bring some people comfort is to run what is called Deviant Statistics. Oops, did not mean to do that. Is Deviant Statistics. Deviant Statistics are really going to now compare your models across one another to see how much adding each predictor to your model is increasing the fit of your model. Meaning, does your newest version of the model have a better fit to the older version of your model? And that's exactly what we're going to do here. we're going to compare from video 1, our unconditional means model, which I have highlighted here, mod 1. We're going to compare it to our other models now, the ones we just created. We're going to compare it to an unconditional growth model with a fixed slope, which is mod 2. And then we're going to compare it to an unconditional growth model with a random slope, which is mod 3, which is the one that shows the biggest drop in the log-like value. And from what we could see from the intervals, shows the most significance amongst the random effects. So the first thing I need to do is rerun the unconditional means model, because when I look at my global environment, it's not here right now. I do not have mod 1 within the data, within my environment, so I need to rerun this again. Here it is all from before. It was all covered in the first video, so I'm not too worried about that. But now we have all three models. Now we have the unconditional model, unconditional means model, the unconditional growth model with a fixed slope, and an unconditional growth model with a random slope. And now we're going to run these deviant statistics, which are all right here. It's just a simple ANOVA, but here we're going to compare model 1 with model 2 to see how much the p-value has changed amongst those log-like values. So let's run it. And we can see the p-value, it is not significant. So when we're comparing those two log-like values, which you can see they're almost identical, which I was saying earlier, the p-value is not significant. There's actually no significant difference between these two models, which is not a good sign, because the first model didn't even have a slope. So by including a slope that is fixed across days of training, it did not increase the p-value, did not decrease the p-value whatsoever. Which is not good, because it just means it's not capturing the fit of the data whatsoever. But now let's compare the next one. Now we're going to run mod 1 and compare it to mod 3, when mod 3 is that unconditional growth model with a random slope. Let's run this now. And of course, it is very significant. It's below 0.05, much below it. So, and you can see from the log-like value that it sharply contrasts from the unconditional means model, which is great. This is pretty much saying at this point to have a slope that is random, which allows for that flexibility amongst individuals, is a much better fit towards the data. And we can see that here between the fixed slope unconditional growth model and the random slope unconditional growth model. They're both much more different. And the random slope is definitely much more significant. So now the next thing, what we could do as an option, is we can run these intraclass correlation coefficients now to see how much we are accounting for clustering within our model. So as you might recall in the first video, when you run the unconditional means model, I've included all the values here just to save time. But if I run the ICC for the unconditional means model, it was about 49. And what it's pretty much saying at this point is that there's a lot of clustering that is taking place in this data. And that's why we decided to do a multi-level model, because the ICC is really suggesting it's a good idea. So the next thing we can do, though, is run the ICC for the next two models. And why I want to do this is pretty much show you what happens once you include a slope within your model to see how much this ICC value could change. So this is the interesting thing here, because when you look at the unconditional growth model with a fixed slope, the ICC was about the same. Didn't really change, and we know it wasn't significant from the unconditional means model. But what is interesting here is that once we add a slope that is random, the clustering has now gone up even higher. Meaning, once we have included a slope that fits the model, we can see we are accounting for a lot more variability of clustering. Clustering is a lot higher, and hence there's a lot more variability in clustering that could be accounted for within this data set. And hopefully within the next video, we'll be able to flush this out even further, where I'll actually be able to tackle the research question itself, where these highlighted sections in green, different job sites, satisfaction with trainer, and overall job satisfaction will now actually be included in the model across the random slope to see how much more of that variability we can account for. Thank you for watching, and stay tuned for the next video where I'll then cover the full model with the research question to really show those differences across individuals. Thank you very much.